light is fast. Travelling at approximately 299,792 kilometers per second, it crosses the distance from the Moon to Earth in about 1.3 seconds, from the Sun to Earth in roughly 8 minutes. Yet the photon you see when you look at the Sun began its journey not 8 minutes ago, but tens of thousands, perhaps hundreds of thousands of years ago, deep within the Sun's core. The path from creation to your eye is not a straight line, but a tortuous wandering through the densest matter in the solar system, a journey that reveals the nature of light, energy, and the nuclear processes that power stars. The Sun's core is an inferno of unimaginable density and temperature. At its centre, roughly 15 million degrees Celsius, hydrogen nuclei collide with enough energy to overcome the electromagnetic repulsion between their positive charges and fuse together. This is nuclear fusion, the process that converts mass into energy, according to Einstein's equation E equals mc squared. 4 hydrogen nuclei, through a series of reactions called the proton-proton chain, combine to form one helium nucleus. The mass of the helium nucleus is slightly less than the combined mass of the 4 hydrogen nuclei, about 0.7% less, and this missing mass is released as energy. The energy emerges primarily in 2 forms: kinetic energy of the helium nucleus and neutrinos, and gamma-ray photons. Neutrinos, ghostly particles that barely interact with matter, escape the Sun almost instantly, streaming through the dense plasma as if it were not there. They reach Earth 8 minutes after their creation, passing through the planet with almost no interaction, billions of them flowing through your body every second without effect. Photons, however, do not escape so easily. A gamma-ray photon born in the Sun's core carries enormous energy, far more than visible light. Its wavelength is a tiny fraction of a nanometer, and it is absorbed almost immediately by the surrounding plasma, a roiling, superheated gas of ionized hydrogen and helium. The photon's energy is transferred to a charged particle, typically an electron, which then re-radiates a photon, often at a slightly lower energy. This process repeats: absorption, re-emission, absorption, re-emission, millions upon millions of times. The path of the photon is a random walk, a drunkard stumble in 3 dimensions. Each time a photon is emitted, it travels in a random direction. The average distance between interactions is called the mean free path, and in the Sun's core it is measured in centimeters. The photon moves a short distance, is absorbed, re-emitted, moves again, absorbed again, in a chaotic dance dictated by probability. There is no preferred direction, no memory of past steps. The photon zigzags through the dense interior, advancing toward the surface on average, but taking an extraordinarily convoluted route. The time required for this journey depends on how you define it. If you count the age of the original gamma-ray photon, it lasts only until the first absorption, a tiny fraction of a second. But if you track the energy, following it as it is absorbed and re-emitted countless times, transferred from one photon to another in an unbroken chain, the journey takes between 10,000 and 100,000 years, with estimates varying depending on models of the Sun's interior. By the time the energy reaches the Sun's surface, the high-energy gamma rays have been converted into lower-energy photons, primarily visible light and infrared radiation, through this relentless process of absorption and re-emission. The Sun is not uniform. It consists of layers, each with distinct properties. The core, where fusion occurs, extends to about a quarter of the Sun's radius. Surrounding the core is the radiative zone, where energy transport occurs primarily through radiation, photons carrying energy outward through the dense plasma. This zone extends to about 70% of the Sun's radius. Here, the temperature and density gradually decrease, but the photon's journey remains a random walk, though the mean free path slowly increases as the plasma becomes less dense. Beyond the radiative zone lies the convective zone, where energy transport shifts to convection, hot plasma rises, cools and sinks, carrying energy upward much faster than radiation alone could. Convection occurs because the opacity of the plasma increases in this region, making radiative transport inefficient. The rising and sinking plasma creates granules visible on the Sun's surface, cells of convection typically 1,000 kilometers across. Energy that took tens of thousands of years to cross the radiative zone traverses the convective zone in a matter of weeks. The photosphere, the Sun's visible surface, is where photons finally escape into space. The temperature here is about 5,500 degrees Celsius, cool compared to the core, but still hot enough to emit light across the visible spectrum. The photosphere is not a solid surface, but a layer of plasma a few hundred kilometers thick, beyond which the density drops sharply, and photons can travel freely without being immediately absorbed. This is the Sun's edge as we see it, the boundary between the opaque interior and transparent space. The spectrum of sunlight reveals its composition. When passed through a prism or diffraction grating, sunlight spreads into a rainbow, but the rainbow is interrupted by dark lines, absorption lines where specific wavelengths are missing. These lines correspond to elements in the Sun's atmosphere absorbing light at characteristic frequencies. Hydrogen, helium, iron, calcium, sodium, each element leaves its fingerprint. By analysing these lines, astronomers can determine not only what the Sun is made of, but also the temperature, density, and motion of different layers. The Sun emits not just visible light, but a broad spectrum of electromagnetic radiation: radio waves, infrared, visible, ultraviolet, X-rays, and gamma rays, each arising from different processes and regions. The photosphere emits primarily visible and infrared light. The chromosphere, a thin layer above the photosphere, emits red light from hydrogen and ultraviolet radiation. The corona, the Sun's outermost atmosphere, is paradoxically much hotter than the photosphere, over 1,000,000 degrees, and emits X-rays. The mechanism heating the corona remains incompletely understood, likely involving magnetic fields and plasma waves. Photons themselves are peculiar entities. They are simultaneously particles and waves, exhibiting properties of both depending on how they are observed. As particles, photons have energy and momentum but no mass. They travel at the speed of light, not merely fast but at the absolute speed limit of the universe. Time, from a photon's perspective, does not pass. A photon emitted by a distant star billions of light years away experiences no time between emission and absorption, though from our perspective billions of years have elapsed. As waves, photons have wavelength and frequency, related by the equation c equals lambda times nu, where c is the speed of light, lambda is wavelength, and a nu is frequency. The energy of a photon is proportional to its frequency. Higher frequency means higher energy. Gamma rays have very high frequency and energy, radio waves very low. Visible light falls in the middle, with red light at lower frequencies and blue at higher. The dual nature of light, wave-particle duality, was one of the great puzzles of early 20th century physics. Classical physics treated light as a wave, and phenomena like interference and diffraction confirmed this. But the photoelectric effect, where light ejects electrons from a metal surface, could only be explained if light came in discrete packets, quanta, whose energy depended on frequency, not intensity. Einstein proposed that light consists of particles, later called photons, and this idea, combined with wave mechanics, led to the development of quantum theory. When a photon leaves the Sun, it travels through space, a near-perfect vacuum, at the speed of light. Nothing impedes it. There are no air molecules to scatter it, no obstacles to absorb it, just the vast emptiness between the Sun and Earth. 8 minutes and 20 seconds after leaving the photosphere, the photon crosses 150 million kilometers and reaches Earth's atmosphere. Here, its journey changes. It enters a medium, a gas thin at first, then increasingly dense, where interactions become possible once more. Earth's atmosphere is a thin envelope of gases held by gravity, composed primarily of nitrogen and oxygen, with traces of argon, carbon dioxide, and water vapor. It extends hundreds of kilometers above the surface, but most of its mass is concentrated in the lowest 10 kilometers, the troposphere. As a photon from the sun enters the atmosphere, it encounters molecules and particles that scatter and absorb light, altering its path and spectrum in ways that shape the world we see. Scattering is the redirection of light by particles much smaller than its wavelength. When a photon strikes a molecule of nitrogen or oxygen, it can be absorbed and almost immediately re-emitted in a random direction. This is called Rayleigh scattering, and it is strongly wavelength dependent. Shorter wavelengths are scattered much more than longer ones. Blue light, with a wavelength around 450 nanometers, is scattered about 16 times more effectively than red light, with a wavelength around 650 nanometers. This is why the sky is blue. When you look at the sky, away from the sun, you see scattered sunlight. The blue light has been redirected by countless molecules, bouncing around the atmosphere before reaching your eyes. Red and orange light, scattered less, tends to travel more directly. At sunrise and sunset, when the sun is low on the horizon, its light passes through a greater thickness of atmosphere. Much of the blue light is scattered out of the direct path, leaving the longer wavelengths, reds, oranges, and yellows, to dominate. This is why sunsets are red. Me-scattering occurs when light encounters particles comparable to or larger than its wavelength, such as dust, pollen, or water droplets in clouds. This scattering is less wavelength dependent, which is why clouds appear white. All wavelengths are scattered roughly equally, and the combination produces white light. Me-scattering also explains the white glare of fog and the bright halos sometimes seen around the sun or moon. Absorption is the capture of a photon's energy by a molecule, atom, or particle. Ozone in the stratosphere absorbs most ultraviolet light, preventing it from reaching the surface. Without this UV shield, life on land would be difficult or impossible. DNA is damaged by UV radiation, causing mutations and increasing cancer risk. Water vapor and carbon dioxide absorb infrared radiation, trapping heat and contributing to the greenhouse effect. Oxygen and nitrogen, the dominant atmospheric gases, are largely transparent to visible light, but absorb at specific wavelengths in the ultraviolet. When a photon passes through the atmosphere without being absorbed or scattered, it continues toward the surface. If it strikes the ground, water, vegetation, or a human-made structure, several things can happen. It can be absorbed, its energy converted to heat. It can be reflected, bouncing off the surface and travelling in a new direction. It can be transmitted through a transparent material, like water or glass. Most surfaces do all three to varying degrees, depending on wavelength and material properties. Reflection is specular if the surface is smooth, producing a mirror image. It is diffuse if the surface is rough, scattering light in many directions. Most natural surfaces produce diffuse reflection. Grass, soil, leaves, skin, which is why we see them from all angles. Specular reflection occurs on still water, polished metal or glass, creating clear reflections. Pigments absorb certain wavelengths and reflect others, giving objects their colour. A red apple absorbs blue and green light but reflects red. Chlorophyll in leaves absorbs red and blue light for photosynthesis and reflects green, which is why plants appear green. The colours we perceive are determined by which wavelengths reach our eyes after being reflected or transmitted by objects. Your eyes are the final destination for photons that have travelled from the sun's core, through the solar interior, across space, through the atmosphere, and reflected off surfaces. The eye is a biological camera, a marvel of evolution refined over hundreds of millions of years. Light enters through the cornea, a transparent dome that provides most of the eye's focusing power. It passes through the aqueous humour, a clear fluid, and then through the pupil, an opening whose size is controlled by the iris, the coloured part of the eye. The iris adjusts the pupil diameter in response to light levels. In bright light, the pupil constricts to about 2 mm, reducing the amount of light entering and protecting the retina. In darkness, it dilates to about 8 mm, gathering as much light as possible. This adjustment, called the pupillary light reflex, occurs automatically, controlled by the autonomic nervous system. Behind the pupil is the lens, a flexible, transparent structure that changes shape to focus light on the retina. The ciliary muscles surrounding the lens contract or relax, altering its curvature. This process, called accommodation, allows the eye to focus on objects at varying distances. When viewing distant objects, the lens is relatively flat. For close objects, it becomes more curved, increasing its refractive power. The retina, lining the back of the eye, is where light is converted into neural signals. It contains two types of photoreceptor cells, rods and cones. Rods, numbering about 120 million per eye, are highly sensitive and function in low light, but they do not detect colour. Cones, about 6 million per eye, require more light but enable colour vision. There are three types of cones, each sensitive to different wavelengths: short, blue, medium, green, and long, red. The brain combines signals from these cones to produce the perception of colour. The process begins when a photon strikes a photoreceptor. Inside the cell, a molecule called retinal, bound to a protein called opsin, absorbs the photon's energy. This causes retinal to change shape, from a bent form to a straight form, triggering a cascade of biochemical reactions. The change alters the electrical charge across the cell membrane, generating a signal that travels through neurons in the retina, bipolar cells, then ganglion cells, and ultimately along the optic nerve to the brain. Retinal is derived from vitamin A, which is why deficiency in this vitamin causes night blindness. The rod cells cannot regenerate the light-sensitive pigment needed for low-light vision. After absorbing a photon, retinal must be converted back to its bent form before it can absorb another photon, a process called the visual cycle. This recycling occurs in cells adjacent to the photoreceptors and takes time, which is why your eyes need several minutes to adjust fully when moving from bright light to darkness. The retina is not uniformly sensitive. The fovea, a small pit near the centre of the retina, contains a high density of cones and is responsible for sharp, detailed vision. When you look directly at something, you're aligning the fovea with the object. Peripheral vision, provided by areas outside the fovea, is less detailed but more sensitive to motion and changes in light, useful for detecting movement and navigating the environment. Remarkably, the retina is wired somewhat counterintuitively. The photoreceptors are located at the back of the retina, facing away from the incoming light. Light must pass through layers of neurons and blood vessels before reaching the rods and cones. This inverted structure is a consequence of evolutionary history, and it creates a blind spot where the optic nerve exits the retina. There are no photoreceptors at this location. You're not normally aware of the blind spot because the brain fills in the missing information based on surrounding context. The signals from the retina travel along the optic nerve to the brain, specifically to a region called the lateral geniculate nucleus in the thalamus, and then to the visual cortex in the occipital lobe at the back of the brain. Here, the raw data from the retina, patterns of light and dark, colours, contrasts, are processed and interpreted. Neurons respond to specific features, edges, orientations, movement, colours. Hierarchical processing combines these features into representations of objects, faces, scenes. Vision is not a passive recording, but an active construction. The brain does not simply receive images, it interprets them, using context, memory, and expectations to make sense of ambiguous or incomplete information. Optical illusions exploit this, presenting stimuli that the brain interprets in ways that conflict with physical reality. The famous Necker cube, which appears to flip between two orientations, demonstrates that the same visual input can be interpreted in multiple ways. Colour perception is also a construction. The photons themselves have no colour. They have wavelengths and energies. Colour is the brain's interpretation of the signals from the three types of cones. The sensation of yellow, for instance, can result from light, with a wavelength around 580 nanometers, or from a mixture of red and green light with no yellow wavelength present, a fact exploited by colour displays, which create the full spectrum of perceived colours using just red, green and blue pixels. The journey of the photon ends not when it strikes the retina, but when its information is integrated into conscious awareness. That integration involves not just the visual cortex, but networks spanning much of the brain. Areas processing motion, spatial relationships, object recognition, emotional significance. Seeing is a whole brain activity, informed by attention, memory, language, and the vast store of knowledge about how the world works. From the nuclear furnace at the sun's core through tens of thousands of years of random wandering, across 8 light minutes of empty space, through the filtering and scattering of Earth's atmosphere, reflected off surfaces, focused by the lens, absorbed by retinal molecules, converted to neural signals, and finally interpreted by the brain, the photon's journey is complete. What began as the binding energy released by fusing hydrogen nuclei ends as a perception, a thought, an experience. Light, in this sense, is not just energy but information, a carrier of structure that links the sun, the earth, and the perceiving mind in a continuous chain of causation. The story of light extends far beyond our own sun. Every star in the night sky is a nuclear furnace, each producing photons through fusion reactions similar to those in our sun, though the details vary with mass, composition, and age. The light from distant stars carries information about their temperature, composition, motion, and distance, and by analysing this light, astronomers have mapped the structure and history of the universe. Starlight begins its journey in stellar cores, where temperatures and pressures are sufficient for nuclear fusion. Small stars like red dwarfs burn hydrogen slowly and can shine for trillions of years. Massive stars burn through their fuel rapidly, living only millions of years but producing far more light and ending their lives in spectacular supernova explosions. The spectrum of a star's light, the distribution of intensity across wavelengths, reveals its surface temperature. Hot stars appear blue, with peak emission in the ultraviolet. Cool stars appear red, peaking in the infrared. Wien's displacement law quantifies this relationship. The wavelength of peak emission is inversely proportional to temperature. A star with a surface temperature of 6,000 degrees Celsius, like the Sun, peaks in the visible range, around 500 nanometers, which corresponds to green light. We perceive the Sun as white or yellow because it emits a broad spectrum, and our vision system integrates all the wavelengths. Hotter stars at 10,000 degrees or more peak in the blue or ultraviolet. Cooler stars at 3,000 degrees peak in the red or infrared. The brightness of a star as seen from Earth depends on 2 factors: its intrinsic luminosity, the total energy it emits per second, and its distance. Luminosity depends on the star's size and temperature, governed by the Stefan-Boltzmann law. The power radiated per unit area is proportional to the 4th power of temperature. A star twice as hot emits 16 times as much energy per square meter. A star 10 times larger emits 100 times as much total energy, assuming the same temperature. Distance diminishes brightness according to the inverse square law. A star twice as far appears 1/4 as bright, 10 times as far, 1/100th as bright. This makes measuring distances challenging, as brightness alone does not reveal whether a star is intrinsically dim and nearby or bright and distant. Astronomers use several methods to determine distances, constructing a cosmic distance ladder that reaches from nearby stars to the farthest galaxies. Parallax is the most direct method, measuring the apparent shift in a star's position as Earth orbits the Sun. Nearby stars shift noticeably against the background of distant stars, and the angle of this shift, measured in arcseconds, allows calculation of distance. 1 parsec, the distance at which a star has a parallax of 1 arcsecond, equals about 3.26 light-years. The nearest star, Proxima Centauri, is about 1.3 parsecs away. Parallax works well for stars within a few hundred parsecs, but beyond that the shifts become too small to measure accurately, even with space-based telescopes. For greater distances, astronomers use standard candles, objects of known luminosity. Cepheid variable stars, for instance, pulsate with periods ranging from days to months, and their period is directly related to their intrinsic brightness. By measuring the period, astronomers determine the luminosity, and by comparing this to the observed brightness, they calculate the distance. Cepheids can be detected in galaxies tens of millions of light-years away, providing crucial rungs on the distance ladder. Type Ia supernovae serve as even brighter standard candles, visible across billions of light-years. These explosions occur when a white dwarf accretes matter from a companion star and reaches a critical mass, triggering runaway fusion that obliterates the star. Because the mass at which this occurs is consistent, the peak luminosity is predictable. Observations of distant type Ia supernovae in the 1990s revealed that the universe's expansion is accelerating, driven by a mysterious dark energy that comprises about 68% of the universe's total mass energy. Redshift provides another distance measure, based on the expansion of the universe. As space expands, it stretches the wavelengths of light travelling through it, shifting them toward the red end of the spectrum. The amount of redshift indicates how much the universe has expanded since the light was emitted, and this relates to distance and time. The most distant observable objects, seen as they were over 13 billion years ago, have enormous redshifts, their ultraviolet and visible light stretched into the infrared. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, has been redshifted from high-energy gamma rays to microwaves with a wavelength of about 1 millimeter, corresponding to a temperature of 2.7 Kelvin. This radiation, detected in all directions, provides a snapshot of the universe when it was only 380,000 years old, and its tiny fluctuations reveal the seeds of structure, the slight variations in density that would grow over billions of years into galaxies, stars, and planets. Photons from the cosmic microwave background have been travelling for over 13 billion years, crossing an expanding universe. When they were emitted, the universe was hot, dense, and opaque, a plasma of protons, electrons, and photons in constant interaction. As the universe expanded and cooled, electrons combined with protons to form neutral hydrogen, and photons decoupled, streaming freely through space. Those photons, redshifted by the expansion, reach our telescopes today, carrying information about the early universe encoded in their temperature and polarization. Not all photons complete their journeys. Many are absorbed along the way by dust, gas, or other matter. Interstellar space is not a perfect vacuum, but contains about 1 atom per cubic centimetre on average, along with dust grains, tiny particles of carbon, silicon, and other elements that absorb and scatter light. This interstellar extinction dims and reddens starlight, making distant stars appear fainter and cooler than they actually are. Astronomers must correct for this effect when studying distant objects. Some photons encounter black holes, regions where space-time is so warped that not even light can escape. If a photon crosses the event horizon, the boundary of no return, it is drawn inward, never to escape. From the perspective of a distant observer, the photon appears to slow down and freeze at the horizon, its wavelength stretched to infinity by the extreme gravitational redshift. Inside the horizon, space-time is so curved that all paths lead toward the singularity at the centre, and the photon's journey ends in a region where the known laws of physics break down. gravitational lensing bends the path of light around massive objects, an effect predicted by general relativity and confirmed by observations. When light from a distant galaxy passes near a massive foreground object, such as another galaxy or a cluster of galaxies, the gravitational field deflects the light, acting like a lens. This can produce multiple images of the background galaxy, distorted into arcs, or even complete rings, called Einstein rings. Gravitational lensing allows astronomers to study distant galaxies, measure the mass of lensing objects, and map the distribution of dark matter. Photons also interact with matter in more exotic ways. In dense, hot plasmas, such as those in the early universe, or in the vicinity of neutron stars, photons can scatter off high-energy electrons, gaining energy in a process called inverse Compton scattering. This upscatters low-energy photons to higher energies, producing X-rays or gamma rays. Conversely, photons travelling through extremely strong magnetic fields can spontaneously convert into particle-antiparticle pairs, and pairs can annihilate to produce photons, processes governed by quantum electrodynamics. The interplay between light and matter structures the universe. Photons transfer energy and momentum, exerting radiation pressure. In stars, radiation pressure counteracts gravity, supporting the star against collapse. In the early universe, radiation pressure prevented matter from clumping until after photons decoupled, allowing gravity to amplify density fluctuations and initiate structure formation. Around black holes, radiation pressure from infalling matter can drive powerful jets that extend for millions of light years, outshining entire galaxies. Understanding light requires understanding quantum mechanics. The photoelectric effect, where light ejects electrons from a material, demonstrates that light comes in discrete packets, photons, whose energy depends on frequency. This cannot be explained by classical wave theory, which predicts that sufficiently intense light of any frequency should eventually provide enough energy to eject electrons. In reality, only light above a threshold frequency, corresponding to a minimum photon energy, can eject electrons, regardless of intensity. This discovery, explained by Einstein in 1905, was a pivotal step toward quantum theory. Quantum mechanics reveals that particles and waves are not distinct categories, but complementary aspects of quantum entities. Photons exhibit interference, a wave phenomenon, yet they are detected as discrete events. The double-slit experiment illustrates this. When light passes through two slits, it produces an interference pattern on a screen, alternating bright and dark bands characteristic of waves. Yet if you detect individual photons, each arrives at a specific point, like a particle. The pattern emerges statistically, as if each photon interferes with itself, passing through both slits simultaneously in a superposition of states. This duality extends to all quantum objects, not just photons. Electrons, atoms, even molecules display wave-particle duality. The wavelength associated with a particle is inversely proportional to its momentum, described by de Broglie's relation. For macroscopic objects, the wavelength is so small that wave effects are negligible, and classical particle behavior dominates. For photons and electrons, wavelengths are comparable to atomic scales, and quantum behavior is essential. Light does not travel alone. It is one form of electromagnetic radiation, part of a spectrum extending from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than atomic nuclei. All electromagnetic radiation travels at the speed of light in a vacuum, differing only in wavelength and frequency. The electromagnetic spectrum is a continuum, with no sharp boundaries, though we divide it into regions for convenience: radio, microwave, infrared, visible, ultraviolet, X-rays, gamma rays. Radio waves have the longest wavelengths and lowest energies. They are produced by accelerating charges such as electrons oscillating in an antenna. Radio astronomy observes the universe at these wavelengths, detecting emission from neutral hydrogen, molecules in interstellar clouds, pulsars, and the synchrotron radiation from charged particles spiraling in magnetic fields. Radio waves penetrate dust clouds that block visible light, revealing regions of star formation and the structure of galaxies. Microwaves, with wavelengths from about 1 millimeter to 1 meter, include the cosmic microwave background and emission from molecules like water and carbon monoxide. Microwave ovens operate at a frequency that excites rotational transitions in water molecules, heating food efficiently. Microwave communication, including Wi-Fi and cell phones, exploits the ability of these waves to carry information and penetrate the atmosphere with minimal attenuation. Infrared radiation, with wavelengths from about 750 nanometers to 1 millimeter, is emitted by warm objects. Everything above absolute zero radiates infrared, with a peak wavelength depending on temperature. Infrared astronomy detects cool stars, brown dwarfs, dust-shrouded galaxies, and forming planetary systems. Infrared cameras reveal heat patterns, useful in night vision, building inspections, and medical diagnostics. The greenhouse effect operates primarily in the infrared, with gases like carbon dioxide and water vapor absorbing and re-emitting infrared radiation, trapping heat in the atmosphere. Visible light, the narrow sliver of the spectrum from about 380 to 750 nanometers, is what human eyes have evolved to detect. This is not coincidental. The sun emits most intensely in the visible range, and the atmosphere is transparent to these wavelengths. Vision evolved to exploit the abundant light available, and the specific range of sensitivity matches the environment. Other animals see differently. Bees detect ultraviolet, enabling them to see patterns on flowers invisible to us. Snakes sense infrared, detecting the body heat of prey. Mantis shrimp have 16 types of colour receptors compared to our 3, though their brains process colour information differently. Ultraviolet radiation, with wavelengths from about 10 to 380 nanometers, carries more energy than visible light and can damage biological molecules. UVB and UVC are largely absorbed by the ozone layer, but UVA reaches the surface, causing sunburn and increasing skin cancer risk. Fluorescent materials absorb UV and re-emit visible light, which is why some substances glow under black light. UV astronomy observes hot stars, active galactic nuclei, and the corona of the Sun. X-rays, with wavelengths from about 0.01 to 10 nanometers, are produced by high-energy processes, electrons decelerating in strong electric fields, atoms in hot plasmas, matter falling into black holes. X-rays penetrate soft tissues but are absorbed by denser materials like bone, making them invaluable in medical imaging. X-ray astronomy requires space-based telescopes, as Earth's atmosphere absorbs X-rays. Observations reveal neutron stars, supernova remnants, accretion disks around black holes, and the hot gas in galaxy clusters. Gamma rays, with wavelengths shorter than 0.01 nanometers, are the highest energy photons. They are produced by nuclear reactions, radioactive decay, particle collisions, and extreme astrophysical phenomena like gamma ray bursts, the brightest explosions in the universe since the Big Bang. Gamma rays require specialized detectors as they pass through ordinary mirrors and lenses. Pair production, where a gamma ray photon converts into an electron and a positron, is one detection method. Gamma ray astronomy has revealed pulsars, blazars, and the annihilation of dark matter candidates. The speed of light is not merely fast but fundamental. It sets the maximum speed at which information and causality can propagate. In special relativity, space and time are woven into space-time, and the speed of light is the same for all observers, regardless of their motion. This constancy has profound consequences: time dilation, length contraction, mass-energy equivalence. As objects approach the speed of light, Time slows for them relative to stationary observers, lengths contract in the direction of motion, and kinetic energy increases without bound. Only massless particles like photons can travel at light speed, and they always do, never at rest, never accelerating or decelerating. Light's finite speed means we observe the universe as it was, not as it is. The sun as we see it is 8 minutes old. The nearest star is 4.2 years in the past. The Andromeda Galaxy, visible to the naked eye, appears as it was 2.5 million years ago. The most distant galaxies observed are seen as they existed over 13 billion years ago, when the universe was young and vastly different. Astronomy is history. Looking deeper into space is looking back in time, reconstructing the past from ancient light. The idea that light has a finite speed was not always accepted. Ancient philosophers debated whether light travels instantaneously or takes time. Galileo attempted to measure the speed of light using lanterns and distant hills, but the distances were too short for human reaction times to detect any delay. The first successful measurement came in 1676, when Danish astronomer Ole Rømer observed the moons of Jupiter and noticed that the time between eclipses varied depending on Earth's position in its orbit. He correctly attributed this to the time light takes to cross Earth's orbital diameter, calculating a speed close to the modern value. In the 19th century, physicists measured the speed of light in laboratories using rotating mirrors and toothed wheels, achieving greater precision. Albert Michelson, whose measurements were the most accurate of the era, found a value within 1% of the currently accepted figure. Today, the speed of light is defined as exactly 299,792,458 meters per second, and the meter is defined in terms of this speed. The distance light travels in 1,299,792,458th of a second. This reversal, defining length in terms of light, reflects the fundamental role of light speed in physics. Maxwell's equations, formulated in the 1860s, unified electricity and magnetism, and predicted the existence of electromagnetic waves. These equations naturally yield the speed of light, revealing that light is an electromagnetic wave, oscillating electric and magnetic fields propagating through space, each generating the other in a self-sustaining dance. This unification was one of the great triumphs of 19th century physics, connecting optics, electricity, and magnetism into a single coherent theory. The medium through which light travels, or more accurately does not travel, was a puzzle. Waves were thought to require a medium. Sound travels through air, water waves through water. Light, observed to travel through the vacuum of space, was assumed to propagate through an invisible substance called the luminiferous ether. The Michelson-Morley experiment, conducted in 1887, attempted to detect Earth's motion through the ether by measuring differences in the speed of a light in perpendicular directions. They found no difference. Light travelled at the same speed regardless of Earth's motion, a null result that puzzled physicists and eventually led Einstein to discard the ether entirely in his theory of special relativity. Light, it turns out, needs no medium. It is a self-sustaining disturbance in the electromagnetic field, propagating through the vacuum at its characteristic speed. Photons mediate the electromagnetic force, one of the four fundamental forces of nature. When charged particles interact, electrons repelling each other, a proton attracting an electron, the interaction is carried by virtual photons, quantum fluctuations that exist briefly, transferring momentum and energy between the particles. These virtual photons differ from real photons in that they can have any energy, not just that corresponding to their frequency, and they exist only during the interaction, constrained by the uncertainty principle. Quantum electrodynamics, or QED, the quantum theory of electromagnetism, describes these interactions with extraordinary precision. QED predicts the magnetic moment of the electron to more than 10 decimal places, making it the most accurately tested theory in physics. The theory treats photons and charged particles as excitations of underlying fields, and interactions as exchanges of photons, calculated using Feynman diagrams, visual representations of particle processes that simplify complex calculations. Light, in all its forms and manifestations, is central to our understanding of the universe. It is the messenger that brings information from distant stars, the mediator of electromagnetic interactions, the energy source that powers ecosystems, and the phenomenon that has challenged and inspired physicists for centuries. From the quantum world of photons and wave functions to the cosmic expanse of light years and redshifts, light connects the smallest and largest scales of reality, a thread woven through the fabric of existence. The interaction between light and matter is what makes the universe visible and knowable. Every observation, every measurement, every image depends on photons being emitted, reflected, transmitted, or absorbed by matter, carrying information about its source and the medium through which it travels. Understanding these interactions reveals not only the nature of light, but also the structure of atoms, molecules, and materials. When a photon encounters an atom, several outcomes are possible. If the photon's energy matches the energy difference between two electron energy levels in the atom, it can be absorbed, promoting an electron to a higher energy state. This is called resonant absorption, and it occurs at specific, discrete wavelengths characteristic of the element. Hydrogen absorbs light at wavelengths of 656 nanometers, 486 nanometers, 434 nanometers, and others, the Balmer series visible in the spectra of stars and nebulae. These absorption lines, dark bands interrupting the continuous spectrum, reveal hydrogen's presence. An excited electron does not remain in a higher energy state indefinitely. After a brief time, typically nanoseconds, it returns to a lower state, emitting a photon. If it returns directly to the ground state, the emitted photon has the same energy as the absorbed one. More often, the electron cascades down through intermediate levels, emitting multiple photons of lower energy. This process, called fluorescence, is responsible for the glow of certain minerals under ultraviolet light, the operation of fluorescent lamps, and the brilliant colours of some biological organisms. Phosphorescence is similar but involves a longer delay. The electron enters a metastable state, where the transition back to the ground state is quantum mechanically forbidden or suppressed. The electron eventually returns, emitting light, but the delay can last from milliseconds to hours. Glow-in-the-dark materials exploit phosphorescence, storing energy from light exposure and releasing it slowly over time. Stimulated emission occurs when a photon passing near an excited atom triggers the emission of a second photon, identical in energy, direction, and phase to the first. This process, predicted by Einstein, is the basis of lasers, light amplification by stimulated emission of radiation. In a laser, a medium with many excited atoms is stimulated by photons bouncing between mirrors, creating a cascade of identical photons travelling in the same direction, producing an intense, coherent beam. Lasers have applications from surgery to communications to manufacturing, and they exploit the quantum properties of light-matter interaction with precision. Scattering, already discussed in the context of the atmosphere, occurs at the atomic and molecular level as well. Rayleigh scattering involves photons interacting with particles much smaller than their wavelength, inducing oscillations in the electrons within the particle. These oscillating charges radiate light in all directions, with intensity proportional to the fourth power of frequency, strongly favouring shorter wavelengths. This is why the sky is blue and why distant mountains appear hazy and bluish. The scattered light between observer and object shifts the perceived colour. Raman scattering is inelastic, meaning the photon loses or gains energy during the interaction. When light strikes a molecule, it can excite vibrational or rotational modes, transferring a small amount of energy. The scattered photon emerges with slightly lower energy, shifted to a longer wavelength. Stokes scattering. Conversely, if the molecule is already vibrationally excited, it can transfer energy to the photon, producing anti-Stokes scattering with a shorter wavelength. Raman spectroscopy exploits these shifts to identify molecules and study their structure, useful in chemistry, biology, and materials science. Compton scattering, where photons collide with electrons and transfer momentum, demonstrates the particle nature of light. The photon's wavelength increases, its energy decreases by an amount that depends on the scattering angle. This effect, discovered by Arthur Compton in 1923, provided direct evidence that photons carry momentum, confirming the quantum theory of light. Compton scattering is significant in X-ray and gamma-ray interactions with matter, relevant for medical imaging and radiation protection. Pair production occurs when a high-energy photon, typically a gamma-ray, converts into a particle-antiparticle pair, usually an electron and a positron. This requires the photon to have energy exceeding twice the rest mass of the electron, about 1.022 mega-electron volts, and it must occur in the presence of a nucleus to conserve momentum. The reverse process, annihilation, occurs when an electron and positron collide, converting their mass into two gamma-ray photons travelling in opposite directions. These processes are central to high-energy physics and astrophysics, occurring in particle accelerators, cosmic rays, and near black holes. Photoionization is the ejection of an electron from an atom or molecule by a photon with sufficient energy to overcome the binding energy. This is the photoelectric effect, and it is the basis of many detection technologies, from photomultiplier tubes to solar panels. In astronomy, photoionization creates ionized regions around hot stars, HEI regions, where ultraviolet photons from the star strip electrons from hydrogen atoms, producing glowing nebulae like the Orion Nebula. Bremsstrahlung, or braking radiation, is emitted when charged particles decelerate, typically when electrons are deflected by atomic nuclei. The energy lost by the electron is emitted as a photon, producing a continuous spectrum rather than discrete lines. X-ray tubes operate on this principle. Electrons are accelerated toward a metal target, and their deceleration produces X-rays with a broad range of energies. Bremsstrahlung also occurs in hot plasmas, contributing to the X-ray emission from galaxy clusters and supernova remnants. Synchrotron radiation is emitted by relativistic charged particles spiraling in magnetic fields. The particles, typically electrons, radiate energy as they accelerate, and the radiation is concentrated in the direction of motion, beamed forward in a narrow cone. Synchrotron radiation produces a polarized, continuous spectrum extending from radio to X-rays, depending on the particle energy and magnetic field strength. It is observed from pulsars, supernova remnants, and jets from active galactic nuclei. Synchrotron facilities, particle accelerators designed to produce intense synchrotron radiation, provide bright, tunable X-ray beams for materials science, biology, and chemistry research. Cherenkov radiation occurs when a charged particle travels through a medium faster than light travels in that medium. The speed of light in a vacuum is an absolute limit, but in materials, light travels more slowly, its speed reduced by the refractive index. If a particle exceeds this reduced speed, it emits Cherenkov radiation, analogous to a sonic boom. The radiation forms a cone, and its angle depends on the particle's speed and the medium's refractive index. Cherenkov detectors identify high-energy particles in neutrino experiments and astrophysical observations. The refractive index describes how much a material slows light. In air, the refractive index is about 1.0003, so light slows by a negligible amount. In water, it is about 1.33, slowing light to about 75% of its vacuum speed. In glass, it ranges from 1.5 to 1.9 depending on composition. The slowing occurs because photons interact with electrons in the material, being absorbed and re-emitted repeatedly, causing a phase delay that manifests as reduced speed. This is also why light bends when entering a medium at an angle, refraction, governed by Snell's law. Dispersion is the variation of refractive index with wavelength. In most materials, shorter wavelengths are slowed more than longer ones, causing different colours to refract by different amounts. A prism exploits dispersion to separate white light into a spectrum. Chromatic aberration in lenses, where different colours focus at different distances, is an unwanted consequence of dispersion, corrected using combinations of lenses made from different materials. Birefringence occurs in certain crystals, where the refractive index depends on the polarization and direction of light. Calcite, for instance, splits an unpolarized beam into two beams with perpendicular polarizations, each traveling at different speeds. Birefringent materials are used in polarizers, wave plates, and liquid crystal displays. The phenomenon arises from anisotropic atomic arrangements, where the electron response to electric fields varies with direction. Metamaterials, artificial structures engineered at sub-wavelength scales, exhibit properties not found in natural materials. Negative refractive index, for instance, bends light in the opposite direction from normal refraction. Cloaking devices, which guide light around an object to render it invisible, exploit metamaterials. Though still in early stages, these technologies demonstrate that by carefully structuring matter, we can control light in unprecedented ways. Optics, the study of light's behavior, underpins much of modern technology. Fiber optics transmit data as pulses of light through glass fibers, exploiting total internal reflection to confine light within the fiber. This enables high-speed internet, long-distance communication, and medical endoscopy. Lasers, lenses, mirrors, diffraction, gratings, and holograms all manipulate light for purposes ranging from entertainment to surgery to fundamental research. Photosynthesis is the process by which life on Earth harnesses the energy of light, converting it into chemical energy stored in the bonds of organic molecules. It is one of the most important biochemical processes, sustaining nearly all ecosystems and producing the oxygen we breathe. Understanding photosynthesis reveals not only how plants capture light, but also how energy flows through the biosphere. Photosynthesis occurs primarily in chloroplasts, organelles within plant cells. Inside the chloroplasts are thylakoids, membrane-bound structures arranged in stacks called grana. Embedded in the thylakoid membranes are protein complexes containing chlorophyll and other pigments. Chlorophyll absorbs light most efficiently in the blue and red regions of the spectrum and reflects green, which is why plants appear green. The process begins when a photon strikes a chlorophyll molecule, exciting an electron to a higher energy state. This energy is transferred through a series of pigments, called an antenna complex, funneling toward a reaction center, where the actual chemistry occurs. There are two main photosystems, photosystem 2 and photosystem 1, each absorbing light at slightly different wavelengths and working in tandem. Photosystem 2 absorbs a photon, exciting an electron that is passed through an electron transport chain, a series of proteins embedded in the thylakoid membrane. As the electron moves, it releases energy used to pump protons across the membrane, creating a gradient. The electron is replaced by splitting a water molecule, a process called photolysis, which produces oxygen, protons, and electrons. This is the source of atmospheric oxygen, a byproduct of photosynthesis that transformed Earth's atmosphere and enabled the evolution of aerobic life. The electron eventually reaches photosystem 1, which absorbs another photon and boosts the electron to an even higher energy. The energized electron is used to reduce a molecule called NADP plus to NADPH, a carrier of high-energy electrons used in subsequent reactions. The proton gradient created by the electron transport chain drives ATP synthesis as protons flow back across the membrane through an enzyme called ATP synthase, a molecular turbine that produces ATP from ADP and phosphate. The ATP and NADPH produced in the light-dependent reactions power the Calvin cycle, a series of enzyme-catalyzed reactions that fix carbon dioxide from the atmosphere into organic molecules. The cycle begins with the enzyme Rubisco, one of the most abundant proteins on Earth, which catalyzes the addition of CO2 to a 5-carbon sugar. Through a series of steps, this produces glucose and other carbohydrates, which the plant uses for growth, energy, and the synthesis of cellulose, starch, and other compounds. Photosynthesis is remarkably efficient at the molecular level. Quantum efficiency, the number of electrons transferred per photon absorbed, approaches 100% for the initial steps. However, overall efficiency, measured as the fraction of total solar energy converted to chemical energy, is typically only a few percent in natural systems, limited by factors such as wavelength mismatch, saturation of photosystems, and energy losses during chemical conversions. Artificial photosynthesis, mimicking the natural process, is an area of active research. Scientists are developing materials and systems that use sunlight to split water into hydrogen and oxygen, or to reduce CO2 into fuels like methanol. These technologies could provide clean, renewable energy, addressing climate change and energy security. Challenges include finding efficient, stable catalysts and matching the complexity and efficiency of biological systems. Photosynthetic organisms vary in their mechanisms. C4 plants, such as corn and sugarcane, have evolved a carbon-concentrating mechanism that reduces photorespiration, a wasteful process where Rubisco reacts with oxygen instead of CO2. C4 plants spatially separate CO2 fixation from the Calvin cycle, concentrating CO2 in bundle sheath cells, where RUBISCO operates efficiently. CAM plants, including cacti and succulents, temporarily separate the processes, opening stomata at night to take up CO2 and fixing it into organic acids, then releasing CO2 during the day for the Calvin cycle, while keeping stomata closed to reduce water loss. Cyanobacteria, ancient photosynthetic bacteria, were the first organisms to perform oxygenic photosynthesis, releasing oxygen as a byproduct. Their activity, beginning around 2.4 billion years ago, gradually oxygenated Earth's atmosphere, precipitating iron dissolved in the oceans as rust-coloured banded iron formations and paving the way for aerobic life. Chloroplasts, the organelles in plant cells where photosynthesis occurs, are descended from cyanobacteria engulfed by early eukaryotic cells in a symbiotic relationship that persisted over hundreds of millions of years. Photosynthesis is not limited to visible light. Some bacteria use infrared light, absorbing longer wavelengths with specialized pigments. Chlorophyll in most plants absorbs primarily red and blue light, but accessory pigments like carotenoids and phycobilins extend the range, capturing green and other wavelengths and transferring the energy to chlorophyll. These accessory pigments also protect against damage from excess light, dissipating energy safely as heat. The energy stored in plants through photosynthesis flows through ecosystems. Herbivores consume plants, obtaining energy and nutrients. Carnivores eat herbivores, and decomposers break down dead organisms, recycling nutrients. At each step, much energy is lost as heat, which is why food chains are limited in length and why primary productivity, the rate at which plants capture solar energy, constrains the total biomass an ecosystem can support. Human civilization depends fundamentally on photosynthesis. Agriculture is the cultivation of photosynthetic plants for food, feed, and fiber. Fossil fuels, coal, oil, natural gas, are ancient sunlight, the stored energy of plants and algae that lived millions of years ago, photosynthesizing and accumulating biomass that was buried and transformed by heat and pressure into hydrocarbons. Burning these fuels releases CO2, returning to the atmosphere carbon that was sequestered over geological time, disrupting the carbon cycle and driving climate change. The journey of a photon from creation to perception encapsulates the unity of the cosmos. Energy, matter, space, and time are interwoven, and light is the thread that connects them. The photon born in the sun's core carries energy from nuclear fusion, information about stellar processes, and ultimately sustains life and consciousness on a planet orbiting 150 million kilometers away. This journey is not unique to photons from the sun. Every photon tells a story. Light from a distant quasar, emitted when the universe was young, reveals the conditions of the early cosmos and the structure of intervening matter. Light from a nebula, glowing as newborn stars ionize surrounding gas, shows the birthplaces of stars and the recycling of material through generations. Light from a candle, produced by combustion, a chemical reaction releasing energy stored in molecular bonds, illuminates a room and casts shadows that have inspired art, storytelling, and contemplation for millennia. The human relationship with light is profound. Vision, our dominant sense, relies entirely on light. We navigate, communicate, and create using visual information. Cultures across history have revered light as a symbol of knowledge, divinity, and truth. The study of light. Optics has driven technological revolutions, from the telescope and microscope to fiber optics and lasers. Understanding light has also driven revolutions in physics, from the wave theory of Huygens and Young to Maxwell's electromagnetism, from Einstein's relativity to the quantum mechanics of Planck and Heisenberg. Light reveals the structure of matter. Spectroscopy, the analysis of light spectrum, identifies elements and molecules, measures temperatures and densities, determines compositions and velocities. It has discovered new elements, mapped the chemistry of stars, revealed the expansion of the universe, and detected exoplanets orbiting distant stars. The absorption and emission lines in spectra are fingerprints, unique signatures that allow astronomers and chemists to decode the universe's composition from afar. Light communicates information. Long before fiber optics and lasers, humans used firelight, lanterns, and eventually electric lamps to signal and illuminate. Lighthouses guided ships, beacon fires warned of danger, and the telegraph used electrical signals, the precursors of modern optical communication. Today, light carries data across continents and oceans, transmitted through fiber optic cables as pulses of infrared light, enabling the internet, streaming video, and instant global communication. Light drives technology. Solar panels convert sunlight directly into electricity using the photoelectric effect, providing clean, renewable energy. LEDs, light-emitting diodes, produce light efficiently, replacing incandescent and fluorescent bulbs and enabling displays, indicators, and illumination. Lasers focus light to cut, weld, and engrave materials, perform delicate surgeries, read data from disks, and probe the structure of atoms and molecules. Cameras and sensors capture light, recording images and detecting phenomena from the infrared to the ultraviolet, extending human perception beyond the visible. Light also marks the limits of knowledge. The speed of light defines causality and the structure of space-time. Information cannot travel faster, and events separated by more than light can traverse are causally disconnected. The observable universe is bounded by the cosmic horizon, beyond which light from more distant regions has not had time to reach us since the Big Bang. We cannot see beyond this horizon, and we never will, no matter how long we wait, because the accelerating expansion driven by dark energy is carrying distant regions away faster than light can close the gap. The future of light-based science and technology is expansive. Quantum communication, exploiting entangled photons, promises secure transmission of information immune to eavesdropping. Quantum computing, using photons to encode qubits, may solve problems intractable for classical computers. Optical clocks, using the oscillations of light to measure time with unprecedented precision, will redefine the second and enable tests of fundamental physics. Telescopes, both ground-based and in space, will observe ever more distant and faint objects, peering back to the era of the first stars and galaxies. Yet the most remarkable aspect of the photon's journey is that it ends in consciousness. The cascade of events, nuclear fusion, radiative diffusion, atmospheric scattering, reflection, absorption by retinal molecules, neural signaling, brain processing, culminates in awareness. You see a sunrise, recognize a face, read these words. The photon, a quantum of energy with no mass and no experience, nevertheless delivers experience, the raw material of thought, memory, emotion, meaning. This is a mystery not yet fully understood. How do physical processes in the brain give rise to subjective experience? Why is there something it is like to be you? To perceive light as colour, warmth as sensation, patterns as understanding? The hard problem of consciousness, as it is called, remains at the frontier of neuroscience and philosophy. Yet it is clear that light plays an essential role. Vision shapes cognition, language, culture. The metaphors of illumination and darkness, clarity and obscurity, seeing and knowing, pervade human thought, because vision is so central to how we engage with the world. The photon's journey, then, is also your journey. You're made of atoms forged in stars, assembled on a planet bathed in starlight, powered by sunlight captured through photosynthesis, perceiving through photons entering your eyes, thinking through electrochemical processes shaped by evolution in a world illuminated by the sun. You are part of the cosmos, not separate from it, connected through light to the nuclear furnaces of stars, the depths of space, and the flow of energy that structures reality. To understand light is to understand much of the universe. It is to see that the sun, though 150 million kilometers away, is intimately linked to your existence. It is to recognize that the past is visible in the night sky, preserved in the light of distant stars. It is to appreciate that the colors of a sunset, the green of a forest, the blue of the sky, are not mere appearances but phenomena rooted in physics, chemistry and biology, explainable through reason and experiment. Light is the messenger, the mediator, the connection. It brings news from the cosmos, energy from the sun, images to the eye, signals to the brain. It has travelled unimaginable distances, endured unimaginable obstacles, and arrived here, now, allowing you to see, to know, to wonder. The photon's journey from a star's core to your eyes is a journey through the fabric of existence, a story written in the language of physics and told in the experience of sight. Every time you open your eyes, you participate in this ancient exchange. Photons created in violence and transformed by chance cross the void and enter your perception, carrying the energy of the sun and the information of the world into the theatre of consciousness. This is the gift of light, not just illumination but connection, not just vision but understanding, not just energy but meaning. The journey of a photon in the end is the journey of knowledge itself, travelling from the heart of a star to the heart of awareness, bridging the gap between the physical universe and the mind that seeks to comprehend it.